Supersonic flows don't often occur in nature. They do occur in wind tunnels like this one at MIT. We're going to look at some effects of compressibility which have to be taken into account whenever we try to produce or control a supersonic flow. The heart of the problem is the behavior of a compressible gas flowing at high speed through a converging, diverging nozzle. We'll begin with the phenomenon of choking, or sonic flow at a throat. We'll encounter shock waves and expansion waves when we come to the supersonic part of the flow. And finally, we'll look at the problem of bringing a supersonic stream efficiently to rest. Because we want to see the whole flow at one time, it's more convenient to demonstrate the same effects in this small channel. Room air at atmospheric pressure enters the channel here, flows from left to right through the channel, through this control valve, and into a vacuum pump downstream. Each column on this manometer board shows the static pressure at the corresponding point on the lower wall, the flat wall of the channel. We've arranged for the mercury level to go down when the pressure in the channel goes below atmospheric. Zero pressure is here. The first column always shows the stagnation pressure upstream, the pressure in the room. The last column always shows the downstream stagnation pressure, just ahead of the valve. At low rates of flow, the pressure is nearly symmetrical around the point of minimum area, called the throat. We can draw a continuous pressure distribution and interpret the curve qualitatively as velocity. This is because viscous forces are not important outside the boundary layers, and the fluid acceleration is determined by pressure forces along. A falling pressure always means a rising velocity, and vice versa. The highest velocity in this flow is at the throat. If we increase this throat velocity, we come to a critical flow rate. The noise level suddenly changes, and the pressure distribution develops a corner at the throat. As we continue to open the valve, the symmetry disappears. Notice that the pressure and velocity upstream of the throat are not changing. Just downstream of the throat, the falling pressure means that the air is accelerating in the diverging part of the channel. Then the pressure rises almost discontinuously, but does not return to its original upstream value. We can see by using a Schlieren optical system to make density variations visible. The mild boiling motion is turbulence in the room outside the channel. Now, watch the throat. As the noise changes, a shock wave appears at the throat and moves into the diverging part of the channel. The position of the shock wave matches the discontinuity in pressure. Here is a close-up of the shock wave forming. The appearance of a shock wave in the channel means that the flow is locally supersonic. Between this symmetrical flow and this unsymmetrical one is that now the velocity is sonic at the throat. This transition to sonic flow at the throat with all of its consequences is called choking. To see why choking plays an important part in compressible channel flow, let's look at the one-dimensional momentum equation for steady flow without viscosity. Notice that changes in pressure and velocity always have opposite sign, no matter what happens to the density. We have already used this fact to interpret our manometer. Here is the same equation rewritten for the special case of reversible adiabatic flow. M is the Mach number, the ratio of the velocity of the fluid to the local speed of sound. For nearly parallel flow, we can also relate changes in density and velocity to changes in channel area by the one-dimensional continuity equation in differential form. Now let's consider flow at the throat, where the area is locally constant. We have two algebraic equations for d rho and dv. Suppose that the Mach number at the throat is not equal to 1. Then the two equations can only be satisfied if d rho and dv are 0. The velocity, density, and pressure are constant near the throat and must be going through a maximum or a minimum there. The flow has a kind of local symmetry about the throat, as in this subsonic case. Now suppose that the Mach number at the throat is equal to 1. This is the special case we have called choking. The two equations are now identical. Since both d rho and dv cannot be determined from a single equation, they need not now be 0 at the throat. The velocity, density, and pressure can increase or decrease continuously through the throat, and the flow need not be symmetrical. In particular, the highest velocity need not occur at the throat. To illustrate these ideas and test the accuracy of the one-dimensional approximation, we have computed some theoretical pressure curves for our channel. The intersection of the curves marks the conditions for which air, accelerating from rest, should reach sonic speed. Note that the decrease in sound level coincides with a change from a symmetrical flow to an unsymmetrical one, as the flow goes sonic at the throat. Downstream of the throat, we have drawn two theoretical curves. The upper branch is subsonic, with the Mach number decreasing from 1 toward 0 as the channel area increases. The flow behaves qualitatively as if the density were constant, so that continuity is satisfied to a first approximation by a balance between area and velocity. In a subsonic flow, the velocity goes down as the area goes up. Here again are the two forms of the momentum equation. In the limit of 0 Mach number, the lower equation shows that the density is literally constant. For this case, we can integrate the upper momentum equation directly. The result is the Bernoulli integral. And we can compute a theoretical pressure distribution for a given flow rate. Even when the real Mach number at the throat is as large as 1/2, as in this example, with a throat velocity of several hundred feet per second, the approximation of constant density is surprisingly good. Now let's go on to look at some properties. The object of the roughness is to produce small disturbances in the flow as an aid in visualization. There is no visible effect on the flow until the shock wave appears. Then characteristic disturbances called Mach waves appear in the region between the throat and the shock wave.